Welcome back to Algebra 2, Chapter 3, Section 4 in this book. Now, I don't want to say that our next topic, linear programming, is not important, because it is. And there's a lot of people who make their living with this idea. But it's not traditionally part of Algebra 2. They just try to give you a little taste of some stuff in case you find it real interesting and you think once you're a math major in college that you want to go into linear programming. Now, this isn't computer programming. This is something else. What it is, it's like businesses try to find the optimal thing for their product, the optimal size or whatever. Like a long time ago, hamburgers like from McDonald's and Burger King and all that came in a certain size. And then they thought, oh, we'll keep selling them for a little bit more money, but we'll make them smaller. We'll make the meat smaller. And I remember honestly getting a hamburger patty on my McDonald's little cheeseburger that was that big. I mean, just tiny. And then Burger King came out with an ad with this little lady yelling, "Where's the beef?" You can probably see it on YouTube. But anyway, so McDonald's blew it. They tried to find the minimum size they could make the patties and still sell, but everybody didn't like them being that big. They wanted their patty to be button size or close to it. So then they started making it bigger again. So optimization, you find, sometimes you want to find the max, and sometimes you want to find the minimum, for something, and how you do it is with computers and with algorithms. But this an easy way to sort of imagine it and sort of start understanding it is that there will be certain constraints. You know, what will the public take, or you know, what are our factors, what we can manufacture and things like that. Like for example, you couldn't have a 50-foot person. The constraints wouldn't work. Our bones couldn't hold us up. So there's only so big a person can be within these constraints. So people are the size they are for a reason. So the region that is good is called the feasible region. Both of these are feasible regions. So graphically, you can either have a bound feasible region or unbound. Now, I want you to look at the examples in your book, but I really only want you to be able to do one problem like this. Other than that, you know, you'll get more of this in college if you become a person who goes into this career. I just want you to know it's out there. But this is what you do. You are given an equation that has C. C equals 3x plus 4, okay? Then you're given constraints, inequalities. Several of them, could be 4, could be 3, and you graph them. So first I graphed x is greater than 0, so I went to x and colored the greater side green. Then I did y is greater than 0, and I colored the greater side of y green, and I really didn't have to worry about them being solid because the lines are the axis, so it didn't matter. And then I graphed this one, x plus y is 8, so I said if x is 0, y is 8. If y is 0, x is 8, I put these 2 points in here, is or equal to, I drew my line, and then to figure out which side to color, I said, what if these are both the origins, 0, 0, then is 0 plus 0 less than or equal to 8? Yes, it is. So I need to color the side that was that included the origin. Okay, that gave me this area that got colored 3 times. And it's this triangle right here got colored 3 times. It is a bound feasible region, and it's got 3 vertices. Do you see that? So what I do is I write down the 3 vertices. I have a pointy part. Vertices is fancy math talk for pointy. Okay, so I got a pointy little area point to my triangle right here at 0, 0, so I write it down. I have one at 0, 8, so I write it down. And I have 8, 0, and I write it down. You just write down all the pointy parts. Okay, next, you take these x and y's and you put them back in your original equation. So I substituted them in. If there's 0, 0, it equals 0. If there's 0, 8, it's 32. And if it's 8, 0, it's 24. Then you look at your answers. The smallest one is the minimum. The biggest one is the maximum. Sometimes they want you to say there is a minimum at 0, 0. There is a maximum at 0, 8. But that's all I want you to know about this. Take a look at it. And if you find this fascinating, you could go into a whole life of working in optimizations in so many ways. There's many ways, all kinds of ways. All right, come back and we're going to do something else new. And this one is more classic Algebra 2, and I think it's interesting. Math is great.